So welcome everyone to the first ever Celo core talk. I'm really excited to be presenting this talk by SPURT on a Randomness Beacon overview. And to kick it off, how it got started, Kobe was really excited to bring over the SPURT team on board to share their research project with the Celo community and the wider Repli audience and stuff. So let's get started. Kobe, you want to kick it off?
Yeah, sure. So I'm really happy that we could hear more about SPURT today. The randomness beacon, or in general, randomness on Celo, is an important topic. It's important both for performance and security of a few of the things that we're running in Celo, like phone number verification. And we always are looking to see how to improve it and how current randomness beacons that are state-of-the-art look like. So it would be really exciting to hear more about SPURT for those purposes and in general. So I think we can get started. So Sarah, you are free to take it.
So you have to enable screen sharing for me. Yeah.
If you need to share the screen, I think I need to make you a co-host, which I can do right now.
Okay.
Let me do it right now. Make co-host. Yeah, you can try right now if you like.
So can you see my screen?
Yep.
The presentation, right?
Yes.
Okay. So hi everyone. I'm Saurav. I'll today talk about distributed randomness beacon, and yeah, this is a joint work with Vineet, Irene, and my advisor Lingren. So we all are from UIC. So briefly, what is a randomness beacon? It's basically we want to emulate this ideal functionality, which is basically some kind of a trusted party which has a clock and it spits out fresh random string after every certain time interval. Like, let's say 3 seconds, it will give fresh random string to everybody, and then it sends the same random string to everybody. So this is the ideal functionality we want to emulate. Of course, we don't have this trusted party. So the goal is to run a distributed protocol, assuming not many of them will be corrupt, and achieve the same functionality. These nodes altogether join forces to generate fresh random string, and the clients will receive those. So this is basically a distributed randomness beacon. And this has many applications in lots of things. For example, you need this randomness for consensus in asynchrony, and that's one of the primary example. You need randomness for crypto. You need randomness even in lots of blockchain setting. You want to choose random validators, you want to partition nodes into random shards. All those purposes you need randomness beacon. You need source of randomness, and you want everybody to see the same source of randomness. So ideally, we can classify the properties that we want from distributed randomness beacon in 4 things. First is unpredictable. So these are intuitive definitions. Unbreakable means that adversary should not be able to guess future random beacons. And why so? Because if adversary can guess, then adversary can possibly strategize in a way that fools the randomness beacon and then gain advantage out of it. So that's why we want unpredictability. We also want bias resistance, that we want the random string to come from a uniform distribution. And we want availability because that's important for applications. So we want that this protocol keeps on generating fresh randomness despite the presence of adversary. And we also want publicly verifiable, public verifiability. That's an additional property that we want to have, because in many of these applications, nodes perform some task depending upon the random string, and they sometimes want to convince others, clients which are not part of the core network, that yes, these tasks were indeed done according to some fresh random string. And that is the notion of public verifiability. And we want any randomness beacon to satisfy this, at least these 4 properties. And yeah, there are many works in this area, and then there are few initial works, and then after blockchain, and a lot of people started working on these. So I'll spend some time on this slide. And so this talk is designed to take questions in between. So feel free to interrupt at any time. I'll be happy to take questions. So we want to classify any randomness beacon primarily in these properties that I list on the topmost arrow. First is a network model. We want to know whether the protocol is safe and live in asynchronous network, or whether it requires synchrony or it requires partial synchrony. So synchrony is the network model where you assume that the message delays are bounded, and the protocol designer knows the message delay a priori before designing the protocol. So if the message delay is delta, so the protocol designer can plug in delta in the description of the protocol. It can say wait for delta amount of time and then do something. In asynchrony, so we do not know, we do not have any bound. Only guarantee it provides is that eventually all messages will be delivered. Like if a honest node sends a message, then eventually that message will get delivered. So that's kind of the strongest network model. So if your protocol is safe and live in asynchrony, so you don't have to worry much about practical network failure and all those kind of things. In synchrony, we need to be very careful about what delta we pick, because often it happens if you plug in a delta in the protocol description and the delta gets violated, that means the network messages are getting delayed more than that delta, then it may violate both safety. Safety means correctness, intuitively means correctness, and also liveness. Partial synchrony takes a middle point in these two extreme scenarios. Asynchrony, working with asynchrony is hard. Synchrony is easy, but sometimes it is not the most practical assumption. So partial synchrony says that as long as network behaves correctly as per expected, we'll make progress. If the network behaves bad, then we don't compromise on safety. We may compromise on liveness. Like the protocol may stall for a while, not produce an output, but it will never do a wrong thing. And practically, you should think of partial synchronous network as networks that are sometimes synchronous and sometimes maybe asynchronous. So that's one of the most crucial parameters for any randomness beacon design. And the next is fault tolerance, which is everybody knows how much adversary we can tolerate. And the remaining 3 properties, whether it ensures liveness, it should be the case. All protocol must be live, otherwise, yeah, it's not useful. And the unpredictability column says whether the randomness beacon, whether an adversary corrupting up to the threshold number of nodes knows the future random beacon or not. The numbers here says the adversary can guess up to t+1 future randomness beacon output. If there's a tick, then say adversary doesn't know any future output. Adversary can only know the current output. Bias
So
resistance says,
Sarah,
yeah.
just this column is actually another way to say this, the look ahead that you have?
Yeah. How much advantage the adversary has. Let's say if you want to use proof of work, then you cannot say, like, if I want to use the output of the proof of work as a randomness beacon, I cannot say I will use the next big block hash as an input to the lottery. It might happen that adversary has already computed the next block and he already knows the hash output. So you want to use something which is further in the future and assume that adversary doesn't know that. Yeah.
Thanks. Cool.
And the next 3 are performance matrix. And we have communication cost, computation cost, and public verification cost. And our main goal is to reduce this communication cost. Yeah, because now we actually have distributed networks, which are, let's say, like few hundreds of nodes that we're interested in. Earlier, in like early days of PVFT, there were centralized entities and they had only 4 or 5 up to 8 nodes or something, very small number of nodes. So communication cost was not so important then. But now, since we are going global, there are systems with hundreds of nodes. There are systems with even thousands of nodes, and we want to the communication cost becomes important. N here is the number of nodes in the network. Lambda is the security parameter, which for simplicity we'll consider to be 256 here. The security parameter varies a lot depending upon what kind of crypto assumptions we are making, like these unique threshold signatures, like the second last column. Depending upon what crypto assumption we make, the security parameter varies a lot. For example, if you assume RSA somewhere, then RSA group elements will be much larger than if we assume only normal DDH. And another crucial column is the last column here, the set of assumptions that we.
One question. What is C?
What is C? Okay, so the Randherd and Algorand are sampling-based approach. And what they say is that you start with a large network and you sample a subset of nodes, and then you run the beacon protocol within the subset. That's the model of these two protocols, Randherd and Algorand. And C is basically after you sample the subset, what is the subset size is denoted by C here.
Got it.
Yep. And yeah, the last column is the setup assumption, which says what kind of initial setup do you need? And we classify it into two parts. So first is the DKG, which is basically you need to run a distributed key generation protocol among nodes. And the disadvantage with that is basically, if you want new nodes in the system, then you have to run DKG, like run a fresh DKG. But the advantage that comes along with DKG is that the costs are much better. The communication cost, computation cost, even liveness. Yeah, you can tolerate asynchrony. For example, the caching is from, I think, 2005. And even then they had a nice protocol, which was kind of the best. But that required DKG. So if you have a system where the number of the nodes are fixed, you don't want to change them often, then it might be better to use DKG, because DKG usually comes with a lot higher cost, like you have n to the n cube log n or n to the 4. So yeah, but if the nodes remain fixed, then you can run the DKG ones and then use a DKG based protocol. DKG based protocol are also simpler, like to think about. For example, if you look at caching at all, it basically says you first do a DKG, and then for every beacon, you use the shared key to sign a new message, and you use the message output as the beacon output, and it's a threshold signature. So yeah, everybody partially signs the message, and you aggregate the message. So that's the caching et al. And Definity DRAN also implements this caching et al. Style protocol. Yeah, with appropriate concrete DKG, concrete signature schemes, and everything. The next block is basically the CRS, common reference string or common random string block. So CRS is with CRS. We refer to CRS as saying each node has access to some initial random string. It could be like two group elements which are chosen uniformly, randomly, and independently. Yeah, it could be few more, like order n, but all those things are random. If you think carefully, there is definitely a circularity here, that we want to generate randomness beacon, but we are starting with some kind of initial random string. And yeah, that we are limited by that as of now. But the thing is, yeah, it might be if you have a CRS that you generate for one of the protocol. Let's say you can generate a common uniform random string by running some kind of multi-party computation protocol. But the advantage of CRS is that once you generate CRS for one protocol, you can probably use it for other protocols as well. But yeah, I'm not saying you should definitely use that, but that's one advantage. And it might be easy to say, if I only want two common random string, let's just hash like millionth bits of pi and then use that as a beacon output. But those may not be secure if an adversary already knows which bit you will be used. But for most practical purposes, you can get initial bits of randomness by doing these kind of things. Here are the third group, which is basically QSDH. This is kind of a strong Diffie-Hellman assumption. And that says, initially you have some structured reference string that you need to generate. Like it could be, the reference string might hide a trapdoor. Let's say it could be of the form g power t square, where t is a trapdoor, some structured referencing. So structured reference strings are slightly harder to generate. Sometimes you need some kind of a setup phase, or you need to run a multi-party computation. Yeah, so QSDA is slightly stronger assumption than CRS. But the advantage of this entire block is these things are reusable. Once you generate a CRS or a QSDA string, you don't have to change this even new party join. You can just use the same thing for the lifetime of the protocol, even though new party join and leave the system. So yeah, this is the state of the art. And BRandPiper, GRandPiper are very new protocol, for example. Okay. So in the second block, we want to highlight the scrape that uses the PVSS, publicly verifiable secret sharing, along with a broadcast channel to generate a distributed randomness beacon. We're highlighting this because we build upon this, like slightly we're inspired from the scrape protocol. And very recently, I think there are protocols which BRandPiper and GRandPiper this is the same author. They can get a very good randomness beacon, but still has lambda and cube communication cost, lambda and square computation cost, but they can tolerate up to half adversary and then ensures liveness, unpredictability, and bias resistance. And where does SPURT stand? So SPURT is a partial synchronous protocol, and it can tolerate up to 1/3 adversary. And it has a communication cost of lambda n square, lambda n square log n plus n cube. And this is the worst case communication complexity. Like if the adversary tries to do active attacks, then this is the communication cost you get. And even in the presence of an active attack, we don't want to we want to still maintain all the properties that we said. We want to maintain liveness, unpredictability, bias resistance, but it comes at a slightly more cost. And it's in the CRS model. It uses PVSS and bilinear pairing.
And what is the complexity in the best case?
So
or in the optimistic?
Yeah, in the normal case, if there are no attacks, the communication complexity is order lambda n square.
Nice.
So yeah, so these log n and nq factors shows up because we need to do some extra step if things doesn't go the way we expect. Yeah, so I'll wait here and let you ask questions on the existing work. I see there are some messages in the chat, but okay. So assuming there are no questions, I'll move ahead. So I have a question. So in which setting is the Celo you are planning to use the randomness beacon, or it's not yet finalized, or you are still
Fair question. So currently we have a random based construction. So sort of a hash chain that is done by proposers in the BFT protocol.
I see.
And we are looking to do something that has less look ahead. And so we're looking at different solutions right now. It could be a DKG based one, it could be any one of the CRS based ones. But basically, if you ask about concrete trade-offs, what would be really good is that producing a new beacon value is very cheap.
I see. Yeah. So from now on, I'll talk about SPURT. And so there are a few key tools that we use. So we use publicly verifiable secret sharing. And our PVSS is based on PVSS scheme of scrape, but we slightly modify it to make it secure against most standard assumption than what Scrape designed. And we use this knowledge of equality of discrete logarithm and state machine replication. State machine replication is, you can say it's the name for blockchain, or blockchain is another other name of state machine replication. And we also use cryptographic multi-signature scheme. So I'll briefly describe most of this primitive. And let's start with threshold secret sharing. I'm sure almost all of you will know about this. A threshold secret sharing scheme is a primitive where we have a dealer, and that dealer has a secret S, and dealer wants to share this secret among different nodes using a n comma t plus 1 threshold secret sharing, such that if the adversary corrupts t nodes up to t nodes, adversary learns no information about the secret S, but t plus 1 honest nodes are sufficient to recover the secret or compute functions on the secret. So this is threshold secret sharing scheme, and one of the popular secret sharing game is Shamir's polynomial-based threshold secret sharing scheme, where the idea is the dealer with the secret S samples a random-looking polynomial where the constant term is secret S, and the remaining coefficients are sampled randomly, and let's call this polynomial p of x. And the shares of each node is basically this polynomial evaluated at the node index. So S1 will be polynomial evaluated at 1, S2 will be polynomial evaluated at 2. Similarly, Sn will be polynomial evaluated at n. And given t plus 1 shares, we can use this Lagrange interpolation, which is a very standard technique to reconstruct the secret. Yeah, that's my 2 minutes on threshold secret sharing. So publicly verifiable secret sharing is again a threshold secret sharing scheme, but with some extra properties. And the properties are that in the threshold secret sharing scheme, in its most basic form, these shares are secret elements, and we don't want to send these shares. We want to send this, the dealer wants to send the share only to the designated receiver. But in PVSS, these shares can be broadcasted to everybody. And why is that? Because the shares are essentially encryptions of the original shares. And if we believe the encryption schemes are hides messages, then even if the dealer broadcasts the encrypted share, others will have no information about the actual plain text share. And the second property that we want is that anyone, even a party which is not part of the protocol, which is not one of these nodes, can verify that the dealer did the sharing phase as per the protocol, or can verify that the message under the encryption is a correct share of some secret S. So this is publicly verifiable secret sharing. I want to introduce few interfaces here. So PVSS scheme has this interface, pvss.share, and it takes in a secret and some public parameters Z and H, and the public keys of all the nodes. So these PVSS schemes do require a PKI. So even in the CRS setting, we do require a PKI, which is stronger than having no setup at all. Yeah. So some people consider PKI is a relatively stronger assumption. Yeah, but but we have PKI for many other different things, so we can probably reuse the same infrastructure for this one as well. So this PVSS scheme do require PKI. The share interface, what it takes a secret and some public parameters and the public keys of each node and generates these three vectors, V, C, and pi. So for notational convenience, I'll use bold letters to denote vectors and non-bold letters to denote normal group elements. So V here is a polynomial commitment, is a commitment to the polynomial that embeds the secret S. C here is a vector of encryptions of shares, and pi is the correctness proof that this encryptions indeed are correct encryptions. Yeah. So The idea is the dealer computes this PVSS shares, VC and pi, and it sends this VC and pi to all the nodes. So each node, upon receiving the polynomial commitment, and can verify individual encryptions, like whether individual shares are correct or not. And it does using this PVSS.verify interface. It takes in the polynomial commitment, it takes in one share, one encrypted share, and one proof, and then outputs either 0 or 1 depending upon whether it is a correct encryption or not. And given decrypted shares, you can again use T plus one of them to deconstruct the secret. So one key property we use, which doesn't come with standard PVSS definition, is the additive homomorphism of commitment and encryptions. That is what we use in SPURT. And the PVSS scheme we design and also the scrape PVSS scheme do satisfy this homomorphism property. The second tool that we use is called knowledge of equality of discrete logarithm. And this is an interactive protocol that achieves the following. So there is a prover and a verifier. There is a common tuple that both prover and verifier knows, which has G, X, H, and Y. These are group elements. And the prover wants to convince the verifier in zero knowledge that the prover knows some alpha such that X is G raised to the alpha and Y is H raised to the alpha. The prover wants to hide alpha, so that's why it uses a zero knowledge protocol. But even then wants to convince the verifier that the prover knows such alpha. And it is important that we focus on the fact that prover knows. This is very crucial for the security of the protocol. So this is one of the standard technique. It's called Chomp-Peterson Sigma protocol, I think. And the protocol is as follows. The prover samples a random field element R and computes A1, which is G raised to the R, A2, which is H raised to the R, and sends A1 and A2 to the verifier. Verifier will sample a challenge, which is E, and send back the challenge to the prover. Prover will compute, depending upon the challenge, a response Z, which is R minus alpha times E. Alpha is the secret here, and sends the response back to the verifier. And the verifier accepts if this equation is satisfied. A1 is G raised to the Z, X raised to the E, and A2 is H raised to the Z, Y raised to the E. And yeah, it might not be immediately clear why this is correct, but if you work out the math, the correctness will follow that. The completeness, which is if the prover is honest, then prover will be able to convince honest verifier. It additionally ensures that the protocol is zero knowledge. The verifier doesn't learn anything about alpha other than whatever is revealed by the public string. And it also ensures knowledge soundness, which says that if a prover can convince you, then the prover must know the alpha. And so although we described this interactive variant of the protocol, we can make this non-interactive using the Fiat-Shamir heuristic. And which says that instead of asking the verifier to send a challenge, the prover can compute the challenge himself by using a hash function or a random algorithm. So this is knowledge of equality of discrete logarithm. Yeah, and if you only want equality of discrete logarithm, you can use pairing based primitive, which we use in our protocol. Yeah. So now I will briefly, I'm just checking time, so I'm okay with time. So the next tool that we use is state machine replication. And yeah, state machine replication is basically the classic name for blockchains. The PVFT paper solves this state machine replication problem. The hot stove and many other papers solve the state machine replication problem. And this problem says this is a protocol among n nodes. N is 3t plus 1 for our setting that agree on a sequence of values or sequence of blocks. This protocol must satisfy these properties. So safety says at any height, all the honest nodes agree on the same value, like decide on the same value. From like drawing an analogy to standard blockchain, that at each height, all honest nodes agree on what is the current block at that particular height. We also want liveness, which is clear, says, so we in our state machine replication, the nodes send their input to the state machine replication, and we say that this protocol is live. If I send the input to the SMR protocol, then the SMR protocol must eventually output this input. For example, in context of blockchain, clients usually send their transaction and say with the liveness requirement is if a client sends a transaction, that transaction should eventually appear in the blockchain, somewhere in the blockchain. We also want public verifiability, which is not particularly required in a state machine replication protocol, but we do want it, which says that whenever a node decides on a value at any given height, then it can prove to others about its decision. So in our protocol, we use a variant of PVFT called Istanbul VFT that has order n square lambda communication per decision. So now coming back to, so we have described all the tools. I'll just wait for 30 seconds to let you ask question if you have any on the primitives that I've discussed so far.
Is this PBFT worst case communication or is worst case cubed?
So that's a very good question. And in PVFT, what do you mean by worst case? So it might happen that you get a sequence of bad leaders, like F bad leaders, and none of those bad leaders do their job. And for each bad leader, you'll have order n square lambda communication. So in the worst case, you'll have, before you produce an output, you'll have n cube communication. But if you, so all the communication costs here are amortized. But if you look at a sequence of n blocks, there could be at most n by 3 bad leaders, but 2n by 3 good leaders will eventually produce an output. So amortized communication cost will be order n square in that case. Yeah. Does that answer your question?
I didn't exactly follow. So if you have, let's say you have like 1/3 bad leaders, why is it n squared amortized?
So let's say each leader can force, each leader can only take up order n square communication cost, n square lambda. So, and honest leader, when this network is synchronous, honest leader will make sure that whenever they are leader, a output gets decided. So if you look at sequence of n rounds, the honest nodes will eventually decide 2n by 3 outputs because there are 2n by 3 good leaders. And the total communication complexity for the entire sequence of n rounds is n cube lambda. So amortize is n cube by 2n by 3 lambda, 2n by 3 n. So you get n squared in that case.
I see.
Yeah. So yeah, in summary, good leaders only take up n square lambda cost and they produce an output. The bad leader may take up n square lambda cost and they may never produce an output, but there are enough good leaders to make this amortized communication cost, yeah, reasonable. So let's talk about SPURT. So it proceeds in epochs, which is basically, let's say, yeah, block height or something, and to draw an analogy. And each epoch has a leader, which is some designated node, and this leader can be chosen using a deterministic protocol. So the leader is only responsible for liveness, not for the safety. So the guarantee, we say that each honest leader's epoch during synchrony produces an beacon output. Why we specify in synchrony? Because in asynchrony, so recall partial synchrony is a network model where the network is sometimes synchronous and sometimes asynchronous, may have arbitrary delays. So when the network is asynchronous, adversary may deliberately delay all messages and you may never produce an output. Yeah, that's the protocol like SMR protocol. But if you use a fully asynchronous protocol, you can still guarantee lots of good things, even periods of asynchrony, like eventual guarantees. But what we say that each honest reader during synchrony will produce a beacon output. And each epoch has 4 phases: commitment phase, aggregation phase, agreement phase, and reconstruction phase. And yeah, during the commitment phase, so I'll just describe the protocol using an example of 4 nodes. The second node here, which is denoted by double circle, is the leader node for that particular epoch. Rest of the nodes are non-leader nodes. So in each epoch, each node will sample a random secret S. Node 1 will sample S1, node 2 will sample S2, and they will compute the PVSS shares for their secret. And this PVSS dot share will produce a vector, 3 vectors, V and C, V, C, and pi. So all the nodes, each node will send the entire vector, all the 3 vectors, to the leader. So each node is sending order n lambda size message to the leader. So it's a all-to-one communication. The leader, upon receiving all the vectors, will validate these messages that these are indeed correct PVSS shares. And why the leader can do so? Because we are using a publicly verifiable secret sharing scheme. The leader can validate for others as well. So once the leader validates t+1 PVSS vectors, let's say here t+1 is 2 because we are operating with 4 nodes, so t can be at most 1. So once the leader validates t+1 PVSS shares, the validated message will look like this. So you have the encryption vector from each node. Each row is a message from each node. So the leader will have 2 encryption vectors, 2 commitment vectors, and 2 proof vectors. So the leader will aggregate the encryption vector and the commitment vector. And aggregation is essentially column-wise multiplication. So the leader will compute C hat, which is the aggregated encrypted vectors, which is basically column-wise multiplication. So what we are doing, the leader is adding the secrets of these 2 parties in the exponent, like under the hood of encryption. So this is an homomorphic property that we are using. And
question?
Yeah.
So at this phase, the leader already does n-squared computation?
Yeah, the computation for the leader is n² for this phase.
Okay.
Yeah, but we use a trick, is that so each node will become leader once in n rounds. So we send the leader these messages slightly before it becomes a leader, so that it gets long enough time to do this computation in parallel to everything else. So amortize, the leader has to do order n, but for this particular phase, if you look at this as a single thing, then it has to do order n², but we amortize this across.
So that's a kind of a pipelining process.
Yeah, it's a pipelining process, yes. So the leader aggregates the commitment vector and the encryption vectors and computes C hat and V hat. The proofs are generated using this Fiat-Shamir heuristics. It uses hash functions, so we cannot aggregate the proofs as of now, but that's okay in our case. Then what the leader does, it computes the Merkle root of the C hat and V hat, and this indexed at I. I essentially represents that from which nodes did the leader computed this commitment vector. So if the leader used the commitments from node 1 and node 2, then I will contain the set 1 and 2. If it is 3 and 4, I will contain the set 3, 4. So I just indicates which all rows did the leader aggregate, and C hat and V hat is the aggregated polynomial encryptions and the commitments. Yeah, this is just an illustration of that. And the leader also computes or takes in this each column, and we call it C bar. Let's say the C2 bar is the encrypted, the column of the second column of the encryption vector. V2 bar is the second column of the commitment vector. Pi2 bar is the proof column. second column of the proof matrix. Yeah, sorry, it's all matrix. And the leader will now send the aggregated polynomial commitment V hat, C hat, and the respective column to each node. This is important here. So the leader will send this column, second column to node 2, send the second column of the commitment matrix to node 2, second column of the proof matrix to node 2. So this is what the leader is doing. Leader is sending some common message, which is V hat and C hat, which is the encrypted messages. Encrypted, it's a polynomial commitment to the aggregated secret and also encryption of the aggregated secret. Additionally, leader also sends individual private messages to each node, V1, C1, pi1 bar to node 1, V2 bar, C2 bar, pi2 bar to node 2, and so on. So all of these vectors are of size order n lambda. So the leader is sending order n lambda size message to each node. Additionally, the leader will send the Merkle root using a state machine replication protocol. So for simplicity, you can think of this as a broadcast channel. The leader is sending the root over a broadcast channel and some common information and some additional individual information to each node. Now, I think you can design the rest of the protocol. It's very straightforward. So each node will receive the root from the broadcast channel and also some private messages. And each node will locally validate that it received valid private messages from the leader. And if it does, then it sends a vote that the leader indeed did his job correctly. So we, in our actual protocol, we have merged this voting phase along with SMR. Yeah, but this is cleaner to think of this in this manner. Like each node will receive the root over a broadcast channel and some private messages and validate that these private messages are consistent with the root and votes for the leader. And
so how can you combine the phases if they need the roots to vote?
So in our actual protocol, in the private message, the leader also includes the root.
Got it.
The leader sends root and everything. So you first check that what you receive is consistent with the root that you received privately. And in the SMR, you vote for that root, vote for the root that you received.
Okay.
So if the leader wants the SMR to find a broadcast channel to finally output the root, the leader has to send consistent root and consistent message to enough nodes, because each node votes in the broadcast channel for the SMR on that particular root that they receive. Yeah. So after nodes validate and agree on the root, and they agree that enough node received like valid shares, each node will decrypt their individual share. Node 1 will decrypt the first element of the C hat vector. Node 2 will decrypt second element of the C hat vector to compute this decrypted message, and then they multicast it to everybody. So this is a single group element, everybody multicast it to everybody else. And once each node receives enough valid shares, so upon receiving a decrypted message, each node uses the pairing based validation check to validate that indeed the decrypted message is a correct decryption of whatever was part of this commitment vector of the ciphertext vector. And upon receiving T+1 valid decryptions, they use Lagrange interpolation to reconstruct the aggregated secret, which is basically addition of secrets of T+1 parties. Yeah. So so far this is the good case or normal case operation of SPURT. So each node sends order n lambda message to the leader sends back order n lambda message to everybody. We run an SMR on a constant size message, and everybody multicast constant size message in the reconstruction phase. So all
So
is
I have
lambda.
I have a quick question. Why are you multicasting the the decrypted shares here and not just sending it to the leader? Is that?
So ultimately what we want that each node, so one of the crucial property of randomness beacon is that it has to be bias resistant. And by that, I mean that once the output is finalized, it should, like every node should learn that output. So if we,
Okay.
one attack that we don't want is one particular node observes the output and may decide that whether everybody else should get it or not. Yeah.
Right. The leader could just drop it. Yeah. Okay.
Yeah.
Yeah. Okay. Thanks.
So yeah, this is the good case operation. So are there any questions, any more questions on this?
I just wanted to do a heads up on time. Yeah, it was just like have 11 minutes left for the call. Just so everyone
yeah.
can rest.
Thanks. Yeah. So there are some additional steps that we need in the reconstruction phase. And that all shows up because of this fact that we are relying on the leader to send private messages to each node. And the leader may not send the private message to some node, and still the entire protocol proceeds. So we want that eventually everybody gets back this private messages or the messages that they should have at the end of a good execution of the protocol. So all those steps will require additional step. Another step, another subtlety is that it might happen that a malicious leader convinces few honest nodes that the broadcast terminated correctly, like the root SMR decision was made correctly, but other honest node may remain oblivious to the SMR decision, that whether we have finalized the output of the broadcast or not. So to accommodate all those facts, we use this multi-signature that says whenever a honest node decides, it sends its decrypted share to everybody else. But if a different honest node receives a reconstruction message, which is basically a decryption of a share, but did not receive the state machine replication decision certificate, which is whether the broadcast is terminated or not, it will ask the sender of the reconstruction message to say, hey, can you give me the state machine replication decision certificate? Because we crucially rely on the fact that each honest node should start the reconstruction only upon observing that the SMR has, the state machine replication has broadcasted the root. And that's a crucial property to ensure bias resistance. So there are a few steps. I'll encourage you to read the paper for the extra steps. But what the extra step gives us, it will increase the communication cost by a factor of this, the second term, f times n plus n plus lambda log n. F here is the number of faulty nodes that are actively doing this attack in the network. And this will increase the communication cost to lambda n square log n plus n cube. And one crucial thing to notice here is n cube term doesn't have this security parameter lambda. Yeah, it might seem not so important, but if you plug in lambda to be 256, then lambda n cube is much higher than simply having n cube. For example, for lambda 256, n cube term is smaller than lambda n square log n for n up to close to 3000. So the dominating term is lambda n square log n. So we do some basic optimizations. We already talked about it. We amortize the leader work by doing pipelining. Everybody sends the commitment vectors to the leader a priori so that the leader gets long enough time to do those things, do the aggregations. We also use existing libraries for computing multi-exponentiation, which is basically says, if you have a vector of group elements, G1 up to Gn, and field elements, A1 up to An, and we want to compute this product, Gi raised to Ai, and then we want to multiply for all I1 to N. There are naive ways of doing this, but using multi-exponentiation, this product can be computed faster than the naive approach. There are, I think, quite a few techniques for doing so. We just use which was available in the library that we used to implement our protocol. So I'll now talk about implementations, experimental setup. Okay, so this is old slide. Sorry, I should have updated things. So we use Golang, and we use IVFT for state machine replication. For curl, we use BLS. Yeah, we do not use 250 ED25519. We use the BLS 12381 because we need pairing. And from multi-exponentiation, we use the same. We use the existing implementation of the BLS 12381 curve. For experimental setup, we run the experiments across 8 AWS regions, 1 node per VM and up to 128 VMs. And we also evaluate the DRAND protocol in the same experimental setup, and also the hydrant protocol in the same experimental setup.
So why would you use the pairings in the DLEQ or?
No, we don't use, we need equality of discrete log in two steps of the protocol, and one requires pairing. In the reconstruction phase, we require pairing.
Okay.
Yeah. So these are new. This is the evaluation. And so for DRAND, so the red curve is the SPURT curve. So we run up to 128 nodes, and this is to beacon per minute. So for example, for 64 node, we see about 42 beacons per minute. We also run DRAND. We try to run DRAND on the same setting, but what we observed is that the DKG phase of DRAND, when we try to run the DRAND for 64 node, doesn't terminate. It throws up some error that we didn't debug, but it was not terminating. One thing which was quite surprising to us is that we expected DRAND to have much better performance than SPURT, because DRAND is very simple protocol. You just send single group element to everybody, and then everybody reconstructs. So although this is what we observe, we believe that if you do a DKG based implementation, the throughput of the DKG based implementation can be improved, much better than SPURT. And for the DRAND evaluation, DRAND currently in the system, they generate one beacon every 30 seconds, but we try to aggressively reduce the delay parameter. Before I say that, I want to say that DRAND and hydrant are synchronous. They require delta in their protocol execution. So currently they take DRAND wants to generate one beacon every 30 seconds. So they make a the estimate for delta is very large for them. That's okay because they want to generate one beacon every 30 seconds. But for our comparison, we try to aggressively reduce this delta as best as we could, and then took this performance. So we see slightly lower than SPURT, but we believe it can be optimized. For hydrant is again synchronous. We try to run in the same setup, but we, in our own observation, got slightly lower performance than what hydrant paper reported. So this blue curve is the numbers from the hydrant paper, because it's again, the experimentation requires fine tunings of delta. We believe we may not have done the best job of choosing delta, and that's the reason we might have seen a slightly lower throughput, but these are the numbers from the original paper. So for bandwidth, this is what we expected. DRAND will have much lower bandwidth than SPURT. Hydrant and SPURT are comparable in terms of bandwidth. It's the total bandwidth per node where we sum the received message and sent message together. And if you are doing a broadcast of let's say one element, then we count it as bandwidth cost of n times lambda. So for each broadcast we multiply with it n. So if you compute the other way, like if you assume broadcast to be sending a single message, then the bandwidth cost will be lower. But currently the bandwidth is considerably larger, like than DRAM. And this is the best case bandwidth. We don't say, I won't say best case bandwidth. This is the normal case operation, for protocol. So we run our protocol in AWS, and in our experimentation, we sometimes see that some nodes are getting delayed for some reason. Yeah, and in those cases, we trigger the worst case scenario, and then we compute the bandwidth, including all the scenarios as well.
So just a question about the bandwidth. So the bandwidth is what each node sees?
Yeah,
or-
it's per node. It's per node
Okay.
sent plus received data, where we count
Okay.
the broadcast as n messages. So I'll speed up a bit because I only have like 1 or 2 minutes. So this is the computation cost measured in an AWS EC2 instance. I think T3 a medium. The aggregation phase is larger. It requires it's in milliseconds. So for n equal to 128 nodes, it requires 6 seconds approximately. And the reconstruction phase is also slightly larger because it involves doing pairing operation. Other phases are relatively smaller, like that. They don't have much, like it's under, few milliseconds, like few hundred milliseconds. And this kind of shows up in the throughput as well. So when we go up to 128 nodes, we only can generate about like 25 to 30 beacons. That's because in the reconstruction phase, each node will spend about fair amount of time doing computation before they send messages. So these all add up. This is the asymptotic. This is the computation cost without any asymptotics, and we just put it in the paper just because to compare computation cost, it'll be unfair if we compare with others because each may depend on the specific implementation. So we just put in concrete numbers here. So I'll just not discuss about this, and you can look at the paper for that. So this is the summary. So we did SPURT, which is a distributed randomness beacon. It provides the properties that we want: unpredictable, bias resistance, available, and publicly verifiable. It doesn't require a trusted setup. But you should note that it requires a PKI and initial 2 random string. It's partially synchronous. It has order n computation amortized, communication lambda n square log n plus n cube, which is again amortized. In the best case, we get lambda n square. And we also improved the PVSS scheme from scrape to so that it is secure under the standard decisional bilinear Diffie-Hellman assumption. And this is again, repeating the existing work slide. So this is, I think that's it.
Okay. Does anyone have any final questions to ask?
So currently I think we have a protocol that can do order n square lambda and in the same setting, even in the worst case. But we didn't write it yet. But I have to make sure some corner cases of the proofs work, but that's something we have. But that uses few techniques that are preliminaries to the protocol, which is basically briefly saying that we kind of know how to do reliable broadcast, which is an asynchronous primitive in communication cost n square lambda, where earlier best was Kashin et al. From 2005, Kashin and Tesaro. I think they require n times n m plus n square lambda log n, and that uses hash functions. Currently, we designed something called asynchronous data replication that can remove the log n factor from the reliable broadcast. And if we remove the log n factor from the reliable broadcast and use some other techniques, then we can get rid of the worst case log n plus n cube factor. So that's something I hope to write soon. And but it has a very similar structure. If you understand SPURT, then that has very minor modifications to SPURT.
So maybe I have like one quick question if we have time yet. So where do you think you would use SPURT versus something that has a DKG plus an SNMR available?
So DKG based primitives are good in terms of communication cost, bandwidth, and everything like computation. But the thing is, DKGs rely on if the set of nodes are fixed for like you don't change the set of nodes that are running the randomness beacon too often, then it might be good to use DKG. Like you do the DKG once, it will cost you something like n to the 4 or n cubed log n, and then you use the DKG based protocol. But the downside of using DKG is that if you change the number of nodes too often, for example, in Algorand proof of stake, in every hide they sample a new committee, you change the committee. Then for those kind of protocols, with every new committee, you have to do a DKG once. So DKG based primitives are not so suitable for those kind of settings. And to compare with sampling based approach, for example, RandHerd and Algorand, so it's sampling. We see sampling as a slightly orthogonal way of scaling things. If you have number of nodes which are in thousands, then you can sample. And once you sample, you still have to run a protocol in the sample set.
Yeah.
So yeah, you can use SPURT after doing a additional round of sampling. Then you can reduce the communication complexity to in terms of C, like instead of N. But we just see it sampling as an orthogonal technique.
Thanks.
Awesome. Does anyone have any final questions? Last chance. I'd like to ask about SPURT. Alrighty, I think then we're at time. I want to thank Saurav and the SPURT team for coming and presenting this awesome overview of SPURT. This is like a recorded call, so we're going to be uploading it to YouTube for everyone else to watch and stuff like that. And we want to thank everyone for coming to participate and asking a lot of questions. And thank you, Kobe, for doing the inviting the team over. Hopefully, we'll do more of this soon. We'll continue where we started from here if everyone likes this format. And yeah, I want to thank you all and take care. Have a good day and thank you, Saurav.
Yeah,
Thank you very much
for having me.
Thank you.
Take care.
Bye-bye.
Bye.
Bye.